This video explains and illustrates how to convert a given number to its IEEE 754 single precision notation. For this example, for this video, I have chosen this example, the conversion of the number negative 8.75 to its IEEE 754 notation. We're going to use single precision notation, which means the notation is only 32-bit. That's basically the same notation that is used in programming languages, float type. So we have two different types normally for representing numbers that have fractions. One is float, one is double. Double has more precision and it's longer compared to the single. So in this example, I'm going to use the single precision, which is 32-bit. Double precision has twice as long as a single precision, which is 64 bits. All right, so to do this conversion, I'm going to use 4 consecutive steps. In these 4 consecutive steps, I will gradually make progress until I construct the IEEE 754 notation. In the very first step, I will write down the given number negative 8.75 in the form of a quotient of dividing an integer by power of 2. That's always the very first step for converting any number to IEEE 754 notation. This number that we have, negative 8.75, will have a representation in the form of dividing an integer over a power of 2. I'll show you how it will look like. But in some cases, when you have numbers that are irrational or they have certain property, it is not possible to write them in the form of an integer over a power of 2. However, you can approximate them using the same format, which means you can say this number, whatever number is given to you, and you want to convert it to IEEE 754 notation. For the first step, you basically say this number is approximately equal to this integer over a certain power of 2. In the second step, we're going to write down the same number, negative 8.75, in binary notation, in base 2, right? But with binary point, which means instead of decimal point, you have binary point, and then you have fractional part, you have the integer parts, and I'll show you how it looks like. In the third step, after you do the second step and you have the binary representation of the number, you're going to convert it to its normalized scientific notation. You may have heard of normalized scientific notation in other classes, like in physics class for representing very big number or very small numbers close to 0. However, here the normalized notation I'm going to show you is a little bit different because it's in base 2. So other than that, it's going to be very similar to the one that you learn in your calculus or physics class, which was base 10 or decimal. After the third step, step 4 would be the last step in which you construct the IEEE 754 notation by building all the fields in this notation. The sign bit, which is 1 single bit, the exponent field, which is 8 bits, and the fraction, which is 23 bits. If this was a double precision notation, then the sign would be only 1 bit, exponent would be longer, 11 bits, and the fraction would be 52 different bits. Because of the longer fraction, you will have higher precision in double precision notation. But we don't want to get into that. It will be very similar to this example. If you do convert a number to single precision by following a similar steps, you can do the conversion to double precision. Let's begin by the first step. Let's jump to the first step. In the first step, I'm going to keep multiplying the number that is given, which was negative 875, by 2 until I reach to either a whole number. In this case, I will definitely reach to a whole number, or sometimes if you don't, then until you reach to the proper precision. The precision for single bit or single precision notation is 23 times or to the power of 23, which means 23 bits of digits after the binary point. But we don't want to get into the details. We're going to just focus on this example. You only need to multiply this number twice by 2 until you reach to a whole number. If you can't reach to a whole number after twice or after 5 times or after 10 times, you may continue up to 23 times, not more than that. Because if you do more than that, you most likely will have no place in the IEEE 754 notation to represent the fractions. So don't multiply it too many times by 2 because you won't need that much of a precision for a single precision notation. All right, so this number, after multiplying it twice by 2, you will get to a negative 35, which is a whole number, an integer. And therefore, you can say the negative 8.75 should be equal to negative 35 over 4 or 2 squared. So I have converted the number in the form of a whole number over a power of 2. That's the first step. Let's jump to the next step, step 2. Given the result of step 1, which was the number is negative 35 over 2 squared, let's convert the number in the form of a binary number with whole number, whole part, and fraction part. To do this, you need to first convert 35 to binary because the numerator was 35. So let's first take care of the numerator, then I'll tell you what to do with the denominator, which is 2 squared. So 35, keep multiplying it by 2 consequently. After multiplying it once by 2, you write down the quotient here, the remainder here. And then for the next step, move the quotient to the next step, and then find its quotient of division by 2 and remainder of division by 2. And keep track of the remainder. We're going to need this. Do this the next time, the next time, the next time, and then the final time where the quotient of division by 2 becomes 0. When that happens, you're going to stop immediately and then read the remainders from bottom to top, from the last step to first step. As you see, this arrow shows the direction of reading the remainders. And that would be 100011 base 2. That's the number 35. And just like decimal numbers, when you have a number, a whole number, you can put a decimal point at the end, right? Just like a number, the whole number, like 25. 25 is the same as 25 dot. So the dot, the decimal point is always at the rightmost location. Same for binary point. The binary point is also at the rightmost location. Now let's take care of the denominator. And the denominator here is 2 squared, which means you gotta shift your number 2 bits to the right, or equivalently move or shift the binary point 2 bits to the opposite direction, to the left. So in order to divide the number that you have negative 35 by 2 squared, you're gonna grab this binary point and shift it 2 bits to the left, which becomes negative 1000.11. Right? Just to give you a better sense of how this, what this means, you can think of it this way. You get the whole part, which is 8, 1000 is 8, and the fraction part, which is 75. You may say, how this 11 is 75? Why? How do you say this is 75? Well, After the binary point, the weight of every bit would be a negative power of 2. So just like the weight of bits before binary point, which were powers of 2, for example, the weight of this one was 1, the weight of this one was 2, the weight of this one was 4, the weight of this one was 8, and that's why we said this number 1000 is 8. When you go to the other side of the binary point, the weights become negative powers of 2, which means 2 to the power of -1 or half, then 2 to the power of -2 or quarter. So the weight of this one would be 2 to the -1, which is half. And the weight of this one would be 2 to the -2, which is a quarter. So because I have 2 ones here, I'm going to add the 2 weights. I'm going to add the weight of the first one and the second one. So by adding these 2 numbers, you get 0.5 plus 0.25, which is going to be 0.75. And that's where we get the 75. But you don't need to be worried about it. As long as you follow the rules of the steps that I told you, you can convert your number to binary with whole part and fraction part. After step 2 is over, we're going to jump to step 3. We're going to use the result of step 2. The step 2's result was 1000.11. Now, what I'm going to do is I'm going to do the normalization. I'm going to create a normalized scientific notation. To normalize a number, you need to move the binary point all the way to the left, where you only have 1 bit before the binary point, and every other bit will be placed after the binary point. So in this case, I'm going to shift the number 3 bits to the right, or move the binary point 3 bits to the left. And that basically means I'm going to scale down my number, right? And because I do that, I have to compensate for it by multiplying it by 2 to the power of 3, or 2 cubed. So the same number that I wrote here, as you see, will be 1.00011. So I move the binary point 3 bits to the left. And to compensate for that, I said times 2 cubed. Right? This is the scientific notation for the number -8.75. That's the result of step 2. In the 4th step, all you need to do is to just build your notation, build your IEEE 754 notation, which is made of 3 fields: the sign, the exponent, and the fraction. So we're going to begin with the sign. The sign is negative, so the binary representation of the sign would be 1. If it was positive, it was 0. Then the exponent. The exponent is 3 because of the way we executed step 3. The result was -1 point something times 2 cubed. Because of the cube, the exponent is 3. But in 754 single precision, you need to add the exponent to make it biased. Add the exponent by 127 to make it biased. And we always store biased exponent. Why? Because this way, negative and positive exponents, after they become biased, they all become unsigned integers, so we can store them as an unsigned number. For double precision, the amount of bias is not 127, it's 1023. So just keep that in mind if you want to do the same operation in the double precision. So I'm going to add this by 127. 3 plus 127 is 130. Then I'm going to write down the binary representation of 130 as an unsigned number with 8 bits of binary, which looks like this. This is a 128 plus 2, which is 130. So that's the 8-bit exponent. We have 1 bit sign. The only remaining piece is going to be the 23-bit fraction. So the fraction is basically this, right? If you ignore the 1, you get 0.00011. We don't care about the items before the dot, before the binary point. Everything after that matters. So we have basically 3 zeros and 2 ones, and that's it. But because it's too short for a 23-bit field, I have to add a bunch of trailing zeros. As you may know, in math, there's no impact of trailing zeros when they are placed in the decimal part, in the fraction part. So you just add, in this case, because I only had 5 bits and I wanted to have a 23-bit, I just added 17 zeros, trailing zeros at the end, and that would create the appropriate length that I want for my fraction bit. So now I have the sign bit, the exponent bit, and the fraction bit. Let's combine these and make this. This is the 32-bit representation. First sign, then exponent, then fraction. And if you want to make it a hexadecimal number, you can basically separate every 4 bits, and then every 4 bits will be represented by 1 single digit in hexadecimal. So this is the final hexadecimal representation of the number, right? All right, so before I end this video, I'm going to just briefly tell you what happens if you have the opposite. If you have the 754 notation, like if you have this yellow box and you want to calculate the number -8.75. So what happens if you want to do the opposite conversion? It's going to be very similar. The sign, first you need to convert this hexadecimal representation to its binary representation this way. Then you're going to break it into 3 pieces, the sign, the exponent, and the fraction. Then you're going to make sense of a sign. Sign would be a negative. This exponent is 130, but this is biased, so you need to subtract 127 from it to get the real exponent. And then you need to make a sense out of the fraction. How do you make a sense out of the fraction? The fraction is 0, 0, 0, 1, 1, followed by 17 zeros. First thing is to drop the fraction, drop the trailing zeros. We don't care about those. Those really don't matter. Second thing is you gotta keep the rest and apply the weight that I mentioned before on them. So as I said, the weights after the binary point become negative powers of 2. So the fraction part is basically here 1.00011, right? And then you just say, all right, so this before this binary point, you have 1, that's good. Then after that, we have 1 bit with the weight equal to, let's write down weight here. The weight is equal to 0.5. The next one would be 0.25, or 1/4, or 1/4, or 1/2 squared, or 2 to the power of -2, whichever you say. I just write down the real value. This one is going to be 0.125. The weight of this one would be 0.0625, if I'm not mistaken. I guess, let's see, 0.6. I guess I'm right. And then the next bit is going to be 0.03125. It's going to be a very long fraction, right? And then you say, all right, so this number is basically the sum of 1. This one's weight is 1, so it's going to be 1 plus the sum of these two. This number plus this number, if you add them together, would be 0.09. Then you have 3. 7.5. And the next step is to say, all right, so the number is 1.09 375 times, I'm sorry, I forgot the sign. The sign should be a negative. So this is a negative number, right? It's going to be negative this times 2q. If you simplify this, you're going to get to the same number, 8.75, negative 8.75. So the number that we get was negative 1.09375 times 2 cubed, which is just simplified using a calculator. It's going to be negative 8.75. All right, so that's pretty much it. Thank you for watching.